Hi friends, this is Naresh. This is my second lecture on mechanics of solids or strength of materials subject. Okay, today in this session I am going to explain about types of loads acting on components and types of stresses and types of strains. Okay, in this session I will explain about these three topics. Okay. Before going to the theory, first of all, you have to know the definition of mechanics of solids or strength of materials. Okay. Now, strength of material or mechanics of solids is that branch of science which deals with the behavior of solid. Okay, behavior of solid materials by studying the distribution of internal forces, the stability and deformation of the materials under the applied loads or forces. Deformation, now I am going to explain about deformation. Deformation is the change in the shape or change in size of the body under application of the force or load. Okay, so deformation is the change in the shape or change in size of the body under application of the force or a load. Oh, okay, here the examples for deformation are change in length, change in diameter, change in width, okay, change in thickness. Okay, now I am explaining with example. For example, here I am considering a body like this. Now I am applying a load. Now I am applying pull loads, two equal and opposite pull loads. Then this is the length of the body or length of the shaft. Okay, if you are applying tensile loads, what happened? The length of this object may increase. Okay, the length of the object may increase due to the externally applied forces. Okay, this change in length, this is a change in length. So here this increase in length or decrease in diameter are called deformation. Okay, when a load is applying on a body, then the body undergo deformation due to externally applied forces. Okay, this delta L is called change in length, this delta D is called change in diameter. Okay, now I am going to explain about strength. What is strength? The internal resistance force offered by the body against the deformation caused due to the application of an externally load is called strength. Okay. Okay. Here also I am explaining with the diagram. Okay. Here also, when you are applying a load on object, okay, when you are increasing a load on object, then the the body will develops internal resistance force. Okay, this internal resistance force is called strength. Okay, this internal resistance force is called strength. The internal resistance force offered by the body to against the deformation caused due to the application of an external load is called strength. Okay, these two loads are called external loads. Okay, the internal developed resistance force is called strength. Now, strength is the ability of a material to resist the externally applied forces without breaking or yielding. Okay, the internal resistance force the internal resistance offered by a part to an externally applied force is called stress. Now, uh, now I am going to explain with example. For example, if you are consider a rod subjected to an external load or force F, okay, if you are consider like this rod, okay, and subjected to external force F at the ends, okay, as shown in figure A, in order to keep the body in equilibrium, the body parts offers opposite reactions like this. Okay, these are the opposite reaction forces or resistance forces to against the possible separation. Okay, now this is the final diagram for internal resistance force. Here these are internal resistance forces. We don't know the amount of internal resistance forces, but our subject point of view, we are considering the amount of internal resistance force is equal to externally applied forces. Okay, now I am going to explain about types of loads. The external force acting on the body is called a load. Okay, this is a body, a load act, yeah, a external force acting on that body is called load. Okay, now types of loads. I am going to explain about types of loads. First one is types of loads broadly classified into axial loads and shear or tangential loads, bending or radial loads. Okay, then after axial loads again classified into tensile or pull loads and compressive or push loads. Okay, these are the types of loads. There are totally 4 types of loads are there: tensile or pull loads, compressive or push loads, shear or tangential loads, radial or bending loads. Okay, these 4 are the types of loads. Okay, these 4 are different types of loads acting on components. Okay, in our subject point of view, these 4 type of loads are very important. Okay, first one, axial load or thrust loads. If the loads are acting along the axis of the body through the center of gravity of its cross section, it is called axial load. Okay, this is a object, this is isometric view, this is a orthographic view. Okay, this shaft shows like visible like this circular halo shaft looks like this. Now if a load is acting along the axis of the component is called axial load or thrust load. Okay, now axial loads are broadly classified into tensile loads and compressive loads. Tensile or pull loads, when a body is subjected to two equal and opposite forces like this. Okay, when a body is subjected to two equal and opposite forces acting away from the body, okay, this is the body, so these two forces are acting away from the body, result increase in length. Okay, result increase in length is known as tensile loads or pull loads. Okay, here you can observe here, this is a component, here the load is acting on the body. Okay, here two equal and opposite pull loads are acting on the body. Okay, so here these two are having same magnitude and same direction, but opposite direction. These two forces are acting along the axis of the object. Okay, Here, the when these loads are acting on the body, result increase in length. Okay, then the length of the object may increase due to the action of these two loads. Okay, these type of loads are called tensile loads. Okay, when two equal and opposite forces acting away from the body, okay, away from the body, then the forces are called pull or tensile loads. Okay, this is a circular body, circular shaft. This is a rectangular bar. Okay, this is a circular or round bar. This is a rectangle or a square bar. Okay, now same compressive strength. When a body is subjected to two equal and opposite forces acting towards the body, okay, when two equal and opposite forces acting towards the body result decrease in length is known as compressive length. Okay, compressive length or push load. Compressive loads are push loads. Okay, this is a round bar when two equal and opposite forces acting towards the object is called compressive loads or push loads. Okay, these are the examples for compressive loads. Here the compressive loads acting on round circular bar. Here the compressive loads acting on rectangular bar. Okay. Shear force also called tangential load. Okay, when a body is subjected to two equal and opposite forces which are acting tangentially, tangentially on any cross-sectional plane of the body, then the force is known as shear force or tangential force. Okay, when two equal and opposite tangential forces acting on any cross sectional plane, then the forces are called tangential loads or tangential force or shear force. Okay, these two forces are equal in opposite direction, but these two forces are acting tangentially. Tangentially means it just touches the body surfaces. Okay, these two forces are not acting on planes, just passing on the surface. Okay, Do- these two forces are not acting on planes. Okay, just touches the surface of the outer surface of the body. Okay, so these two forces are called shear force or tangential forces. Okay, this is an example for cube. Okay, here the force just touches the top surface. Okay, now this force just touches the bottom surface. Okay, these two forces are not acting on the planes. Okay, these two forces just passing through outer surface. Now radial load or normal load or bending load. Okay, radial loads. If the loads are acting perpendicular to the axis of the body, results in bending in length is known as radial loads or normal loads or bending loads. Okay, if the loads are acting perpendicular to the axis of the body, okay, it is very important. If the loads are acting perpendicular to the axis of the body, results in bending in length is known as radial loads. Radial loads also called as normal loads or bending loads. Okay, this is the example for a round bar. Okay, this is the axis of this shaft, and this is the load. here the load is acting on the body. This the angle between load and axis of the body is 90 degrees. Okay, so uh, so if the loads are acting perpendicular to the axis of the body, okay, then those loads are called normal loads. Normal loads are radial loads or bending loads. Okay, so this is a body, this is the axis of the body, and here the angle between load and axis is 90 degrees. So this is a normal load or radial load. Okay, now I am going to explain about a very important topic, that is a stress. Okay, stresses. What is stress? The internal resistance force offered by the body against the deformation per unit cross-sectional area. Per unit cross-sectional area is called stress. Okay, the internal resistance force offered by the body. Okay, the internal resistance force offered by the body against the deformation. Against the deformation per unit cross-sectional area is called stress. This is a body. Okay, now this is the cross section. Okay, the cross section here is a circular cross section. Okay, so here the load is acting on a plane, that is load is acting on cross section. This is F is the load. Okay, F is a load. This is a tensile load. Okay, tensile load means the load acting away from the body. Okay, this is also equal and opposite tensile load. Okay, here here the stresses are denoted by the symbol sigma. Okay, sigma is the symbol for stress. Okay, now the formula for stress is internal resistance force by cross sectional area. Okay, or stress is equal to load by cross sectional area. Okay, here the internal resistance force is equal to the external applied force. Okay, we don't know about the amount of internal resistance force. Okay, just for our problem, for our subject point of view, we considered internal resistance force is equal to external applied force. Okay, so this is the formula for stress. So the formula is sigma. Sigma is the symbol for stress. Sigma equal to F, force by cross sectional area. Okay, this is the formula for stress. Now I am going to explain about units for stress. Yeah, already we discussed about stress definition, that is stress equal to internal resistance force or external force divided by cross sectional area. Okay, the formula is sigma equal to F by A. Okay, here F is the force or load. Okay, the units for force or load is Newton. Okay, Newton is the unit for force. Now A is the cross sectional area. Here the cross sectional area is in mm square or meter square. Okay, the units for area is mm square or meter square or centimeter square. Okay, now sigma, therefore sigma equal to load by area. Load by area equal to the load in Newton and area in meter square. Okay, therefore the units for sigma equal to Newton per meter square. Or if the area in mm square, then the units for stress equal to Newton per mm square. Okay, these two are the units for stress. But 1 Pascal, this is 1 PA. PA means Pascal. 1 Pascal equal to 1 Newton per meter square. Okay, this unit 1 Newton per meter square value is equal to the 1 Pascal. Okay, this Pascal is the unit for stress. Okay, Here the units of stress equal to units of pressure. Same. The units are same. The units are same for pressure and stress. Okay. Pascal is the units for pressure. Okay. So 1 Pascal equal to 1 Newton per meter square. Okay. So 1 Pascal equal to 1 Newton per meter square. And now 1 kilopascal equal to, kilo means 1000 Pascal. So 10 power 3 Newton per meter square. As well as 1 megapascal equal to 1 mega means 10 power 6. So 10 power 6 Pascal equal Newton per meter square. If you want to convert these values in mm, okay, then 1 megapascal equal to 1 Newton per mm square. Okay, 1 megapascal equal to 1 Newton per mm square, or 1 megapascal equal to 10 power 6 Newton per meter square. Okay, similarly 1 gigapascal, where capital G means giga, capital M means mega, capital K means kilo. Okay, so 1 gigapascal equal to 10 power 9, 10 power 9, 1 giga equal to 10 power 9, Pascal equal to Newton per meter square. Whereas if you want to convert this 1 gigapascal into mms, okay, then 1 gigapascal equal to 10 power 3. You have to cancel 10 power 6. Okay, so 10 power 3 Newton per mm square. So in mms, the value is 10 power 3 Newton per mm square. So these all are units for stress. Okay, now now I am going to explain about types of stresses. Stresses broadly classified into normal stresses and shear or tangential stresses and bending stresses. Okay, then after normal stresses, again classified into tensile stresses and compressive stresses. So these four are the type of stresses considered in our subject. Okay, tensile stress, compressive stress, shear stress, bending stress. Shear stress also called tangential stress. Okay, so there are totally four types of stresses are there. Okay, in next slide I will explain one by one. First, tensile stress. What is the tensile stress? The stress induced in a body. Okay, the stress induced in a body when subjected to two equal and opposite pull loads. Okay, the stress induced in a body when subjected to two equal and opposite pull loads. Okay, these two are pull loads. Okay, the stresses induced in a body when subjected to two equal and opposite pull loads, as shown in figure, as a result of which there is an increase in length. Okay, there is an increase in length and decrease in lateral dimensions, is known as tensile stress. In tensile stresses, when you are applying pull loads, the length of the object or length of the component may increase. Okay, and the other dimensions are may decrease. Okay, so the formula for tensile stress is equal to tensile load or pull load divided by cross section area. Here the cross section area of this shaft is this one. Okay, this is the cross sectional area. Okay, so here the cross sectional shape is circular shape. Okay, now this is the formula for stress. Okay, sigma T. Sigma T means tensile stress. Sigma is the symbol for stress, and T is the tensile. So tensile stress is equal to load by area. Here the positive sign indicates tensile loads. Okay, here the positive sign indicates tensile loads. That means here the length of the object increases when you are applying loads. Okay, that's why you have to consider positive sign in tensile stresses. Okay, Now coming to the compressive stress. The stresses induced in a body when subjected to two equal and opposite push loads. Okay, these two are the push loads. Okay, these two are equal and opposite in direction and acting along the axis of the shaft. Okay, along the axis of the component. Okay, and as a result of which there is an decrease in length and increase in lateral dimensions. Okay, increase in lateral dimensions is known as compressive stress. Okay, here this is the length from here to here. This is the length of the component. When you are applying a compressive forces or compressive or push forces, then the length of the component may decrease. Okay, and the other dimensions, that is the diameter of the component, may increase. Okay, so the formula for compressive stress. The formula for compressive stress equal to compressive load or push loads divided by cross sectional area. Okay, this is the formula for compressive stress. Here the units are same for stress. Okay, here the compressive stress sigma indicates stress and C indicates compression. So compressive stress is equal to minus F by A minus load by area. Here the negative sign indicates compressive loads. Okay, here negative sign indicates compressive loads. Okay, when you are applying compressive loads on body, the length of the component may decrease. Okay, that's why you have to consider negative sign for compressive loads. Okay, yeah, negative sign for compressive loads. Now coming to the another type, that is a shear stress. The stress induced in a body when subjected to equal and opposite forces acting tangentially. Okay, acting tangentially across the resting section. Okay, these two forces are acting tangentially to the this body. Okay, the results its results body tends to shear off across the section is known as shear stress. Okay, here the formula is the same. Shear stress is equal to shear load or tangential load by resisting area. Okay, this is the formula for shear stress. Shear stress equal to shear load or tangential load divided by resisting area. Okay. Now here the shear stress is indicated by symbol tau. Okay, this is the symbol for stress, shear stress. Okay, the symbol uh, tau equal to force or load by resisting area. Okay, this is the another example for shear stress. Here, these two forces F and F, these two forces are equal and opposite in direction, but these two forces are acting on the surfaces, top surfaces of the body. Okay, here these two forces are not acting on the planes, just touches the body. Okay, so this one is the another example for shear stress. Here I consider two plates. For joining these two plates, I am using a riveted joint. Okay, I am using a riveted joint to join these two plates. When you are applying two forces equal and opposite directions like this, then the rivet may fail due to shear. Okay, now coming to the last type, that is the bending stress. The stress induced in a body when subjected to bending loads is known as bending stress. Here, this is the a rectangular body or rectangular component is fixed into a wall. Okay, so this component is fixed into a vertical wall. Okay, I fixed this component at this wall. So now I am applying a vertical load on this component. Then what happened? Okay, here you can observe here when a load is acting on the body, then this component may fail due to bending. Okay, so here the this type of load is called bending loads. Okay, bending loads are normal loads. Okay, the stresses induced in a body when subjected to bending loads is known as bending stress. Bending stress having different formulas, so that's why I am not writing the formulas. In second unit we will discuss about bending stress. Okay, now coming to the types of stresses. So sorry, now I am going to explain about strain. What is strain? When a body is subjected to some external force, there is some change of dimension of the body. Okay, so the ratio of change in dimensions to the original dimensions of the body is known as strain. Okay, the ratio of change in dimensions of the body to the original dimensions of the body is called strain. Okay, so it is denoted by symbol epsilon, epsilon or e, small e. Okay, strain has no units because here the numerator is in length and denominator also is in length. Okay, you can observe here the formula for strain equal to epsilon equal to change in dimension by original dimension. Okay, here if the dimensions change in dimensions are in mm. Okay, the units for a dimension is mm or meter. Okay, now original dimensions also in same units. Okay, that's why the numerator and denominator may cancel. Okay, so therefore the strain has no units. Okay, so therefore the strain has no units and the symbol for strain equal to epsilon. Okay, it is very important. Now I am going to explain about different types of strains. Okay, and strains broadly classified into lateral strain, linear or longitudinal strain, and this one is a tensile strain, this one is a compressive strain, this one is a shear or tangential strain, this last one is volumetric strain. Here total there are six type of strains are there. Okay, I will explain one by one with examples. When yeah, lateral strain, yeah, the strain produced by stresses is called uh, tensile strain or compressive strain or shear strain. Okay, if when uh, if the strain produced by tensile stress, okay, if the strain produced by tensile stress is known as tensile strain. Okay, if the strain produced by compressive stress, okay, then it is called compressive strain. If the strain produced by shear stress, then it is known as shear strain. Okay, if the deformation is in length, if the deformations is in length, then it is called linear strain. if the deformations in other than length is called lateral strain. Okay, now I am going to explain about these topics. Linear or longitudinal strain, the ratio of change in length, the ratio of change in length to the original length of the body is known as linear strain or longitudinal strain. Okay, the ratio of change in length to the original length of the body is called linear strain or longitudinal strain. Okay, longitudinal or linear strain is equal to change in length by original length. Here the formula is plus or minus delta L by L. Okay, this is the original shape of a object. Okay, I consider this one as a original shape. Okay, this is the original diameter. Okay, before loading the size of the bar equal to D. Okay, the diameter of the bar equal to capital D and length, original length equal to L. Okay, now I am applying tensile loads on this body. Then the length of this object may increase like this. Okay, the change in length is called delta L. This increase in length is called change in length, that is the delta L. And the diameter of this component may decrease due to the tensile loads. Okay, the change in difference of diameters is called change in diameter. Okay, so this one is a change in diameter, this one is a change in length. Okay, when you are applying tensile loads on a body, the length of the body may increase and the diameter of the body may decrease due to the tensile stresses. Okay, in this particular case, the length is increased, diameter is decreased. Okay, so now I am applying compressive loads on the same body. Okay, if I am applying compressive loads on this body, what happened? The length of the body may decrease and the diameter of the body may increase due to the compressive forces. Okay, so delta L is the change in length and delta D is the change in diameter. Okay, now here the positive sign for tensile loads and negative sign for compressive loads. Okay, because here the length of the component, here in this case the length of the component may increase, in this case the length of the component may decrease. Okay, that's why here in this case for compressive loads you have to consider minus sign. In tensile loads you have to consider positive sign. Okay, so the ratio of change in length, that is a delta L by original length, that is L, is called linear or longitudinal strain. Okay, there is no units for strain. Okay, now lateral strain. The ratio of change in lateral dimensions to the original lateral dimensions of the body is known as lateral strain. Okay, the formula is same for all strains. Strain equal to change in dimension by original dimension. But in lateral strain, the ratio of change in lateral dimensions to the original lateral dimensions of the body is called lateral strain. Lateral dimensions means other than length. Okay, other than length dimensions are called lateral dimensions. So for this case, already we have explained in previous slide. Okay, here if you are applying a tensile load, then the diameter of the component decreases. Okay, here in this case, if you are applying compressive loads, then the diameter of the component may increase. That's why in this case you have to consider negative side, in this case you have to consider positive side. Okay, the formula is same. The lateral strain equal to change in lateral dimension by original dimension. In case of circular shafts, the lateral dimension is diameter. Okay, delta D by D. Okay, in case of rectangles, Here negative sign for tensile loads, positive sign for compressive loads. Okay. Here for circular shafts, small d or capital D is the lateral dimension. Okay. Other than the length, other than length dimensions are called lateral dimensions. So here for shaft having only two dimensions, that is diameter of the shaft and length of the shaft. So if the strain is represented in terms of diameter is called lateral dimension, lateral strain. Okay. So here the change in diameter by original diameter is called lateral strain. Okay. In case of rectangle or square components, uh, it having three dimensions, that is length of the component, width of the component, thickness or height of the component. So here the lateral dimensions are width and thickness. Okay, width and thickness are the lateral dimensions. Okay. So in lateral strain for this component, change in width by original width. Here W is the width, W is the original width. So change in width equal to delta W by W. Okay, and lateral strain for in terms of thickness, change in thickness by original thickness, that is delta T by T. Okay, these two are the formulas for this component. This formula is used for this circular sections. Okay. Now tensile strain. The strain produced by tensile stress is known as tensile strain. Okay. The strain produced by tensile stress is known as tensile stress, tensile strain. In this case, the load, in this case, the tensile loads, tensile to equal and opposite tensile loads are acting on the object. Okay. This is the original shape of the object. Here, this is the original diameter of the component, and this is the original length of the object. Now I am applying the tensile loads on the object. Here these two are equal and opposite forces. Okay, when you are applying tensile loads, then the length of the component increases and the diameter of the component decreases. Okay, so here the lateral strain equal to delta L by L, linear strain equal to delta L by L. Here the positive sign you have to consider, because here the length is increased, and lateral strain equal to delta L by L, delta D by D. Delta D by D is the lateral strain. Okay, here the diameter of the component decreased, so that's why you have to consider minus sign. Okay, this is the tensile strain. Okay, these two formulas for tensile strains. Same as compressive strain also. If you are applying two equal and opposite push loads on the component, then the body may the length of the body may decreases, and height and other lateral dimensions may increase. That's why the strain produced by compressive stresses is known as compressive strain. Okay, these tangent strain, compressive strain, lateral strain, linear strain, whatever it may be, strain has no units. Okay, here this is the components. Capital D is the original diameter, capital L is the original length. Now I am applying the compressive forces on the body. Okay, then when you are applying the compressive forces, then the length of the component decreases and the diameter of the component increases. Okay, this is the change in length, this one is the change in diameter. Okay, here the diameter of the component increases, so you have to consider positive sign for lateral strain, and the length of the component decreases, so you have to consider negative sign for linear strain. Okay, here the linear strain equal to negative sign because the length of the component decreases. Here lateral strain, here positive side, positive delta D by D. Here the diameter of the component increases. So that's why you have to consider positive sign. Okay. Now shear strain. The strain produced by shear stress. The strain produced by shear stress is known as shear strain. Sorry, This is shear strain. Okay, the shear strain is denoted by symbol pi. It is the angle deformation. Okay, shear strain is the angle deformation. That's why I am taking this shear strain in terms of angle. Okay, now when a body is subjected to two equal and opposite tangential forces, the angular deformation takes place. Okay, like this is the initial position of the component. When you are applying these two tangential forces, then the shape may comes like this. Okay, so the angular deformation per unit length is known as shear strain. Okay, the angular deformation per unit length is called shear strain. So this is the original shape of the component before loading. Okay, this is the height of the bar. When you are applying tangential forces on this component, then the shape goes like this. Okay, this is the deformed shape after loading. Okay, here this is the initial position, this is the final position of the component. So the angle between initial position and final position is called this angle pi is called angular deformation. This angular deformation is called shear strain. Okay, if you are considering this triangle, okay, by using trigonometry formulas, applying tan pi equal to by using this triangle, tan pi equal to opposite side, tan pi equal to opposite side, that is a delta L. Opposite side means a change in length divided by adjacent side. The adjacent side is original length. So the formula for angular deformation is equal to change in length by original length. Okay, uh, if you are neglecting this tan theta, then pi equal to delta L by L. Delta L by L is called strain, shear strain. Okay, this is the formula for this shear strain. Okay, shear strain equal to change in length delta L by original length. Okay, now the last topic is volumetric strain. The ratio of change in volume to the original volume of the body is known as volumetric strain. Okay, it is also denoted by symbol epsilon. uh, Volumetric strain also having no units. This is the shape of the component. Here you have to consider three-dimensional object. Okay, if you want to find the value of volumetric strain, you have to consider three-dimensional object only. Okay, for three-dimensional objects, you have to consider volume. Okay, so that's why for volumetric strains, you have to consider three dimensions: length, height, and width. Okay, this is a rectangular block. Okay, having length L, width W, and height H. If three forces F1, F2, F3 are acting on that volume, then it may compress or elongated. Okay, so the volumetric strain equal to change in volume by original volume equal to delta V by V. Here positive sign is for tensile loads. Okay, when you are applying tensile loads, then the component may elongate it. Okay, if you are applying compressive loads, then the component may compress. Okay, that's why for compressive loads you have to consider negative sign. For tensile loads you have to consider positive sign. Okay, okay, okay. Thank you. If any doubts, please ask me.